Hi, everyone. Thanks for coming to this presentation about LettuceWrap, an interactive language interpreter. My name is Spencer Wilson. I am a student in our Object-Oriented Analysis and Design course here at CU Boulder and a past instructor of our Principles of Programming Languages course, which is the inspiration for the language Lettuce that you'll be seeing in this video today.
Hi everyone, I'm Reese. I'm also a student in OOAD in the spring of 2023. I'm interested in how we can apply Scala to real-world applications. So this is what we did for our final project is we made an interactive language interpreter called LettuceWrap. And today we'll walk you through its functionalities. We'll tell you a little bit about it and motivate why we decided to design this tool.
So a bit about how we separated our workload. I worked a lot on our backend and the Scala code, working on the interpreters for the product. And we worked together on how to collaborate between the Scala backend and a front end in React and Material UI. I'll let Reese talk more about the front end framework.
Sure. So start out, we built the repo with a React Material UI boilerplate project, and then also a Scala Play backend. So our hope was that we can have the communication happen between them, meaning that we can make this into a deployable web application. I have a lot of experience working with React in web applications, and I really enjoy using frameworks like Material UI, which are really useful for providing template components for your web app. And so a lot of the work that I was involved in was designing, the input box, the buttons back for submit that we'll go through in a second, and having them work together to map to on-click functions, which actually would communicate to the back end and send information back and forth. So Spencer actually has it pulled up, and we'll take a look.
Yeah, so if you're interested in running our product, in the README is a quick instructions manual. You'll need to execute our backend as well as the front end. There are advanced notes if you're interested, and you do need to read the full notes the very first time that you're running it. We go to React app, npm start. This launches the app for us. Beautiful. You also want to go ahead and boot up the backend. Go to Scala backend, svt run. Having already compiled the code. And it should be working for us. So Reese, tell us more about what all these boxes are.
Yeah, so these are the various components. They're organized like so, where we have an app bar at the top. So basic HTML, welcome to the LettuceWrap. It might actually be iterated on by the time you see this video. We're planning on continuing development of this project afterwards for use of other classes and so on. We'll talk about applications later. The first component you'll see is actually that expression box where the user can input things to be evaluated and step through. And the send, the back, and the next are also in that component too. So those are buttons included in that one section. So the send, we'll send it as an object to the back end, which we've used actually JSON as our data structure just to be stored in memory. To be manipulated, it separates out steps so we can see a lazy or eager evaluation. This is actually toggleable on the front end by the user if they want to switch between lazy or eager conditions. They can do it with these drop-down menus here. Also next to that, you see the type conditions and then also the scoping conditions. So we can do none or implicit with the type conditions. In the scoping conditions, we can do lexical static or dynamic. So there's actually a lot of options for this grammar to process your expression. So you'll see on the bottom left here, we'll have the expression output. And as you hit next or back, this will step through the expression output on the right. And you can evaluate. So what Spencer's doing right now, we see on the left-hand side, we start out with 1 plus 2 times 3. If he hits next, it returns, this is actually 1 plus 6 is how this is evaluated. And if he keeps clicking through next steps, the left-hand side will update as well. So you can imagine this is useful for a student who would like to step through the logic of an evaluation behind the Scala computer language and understand how the processes are ordered.
A more interesting example than 1 plus 2 times 3 that you may want to see, consider let x equal 1 plus 2 in, let f equal a function of y, x plus y in, let x equal 20 in, f of 0. Depending on scoping conditions, this changes quite dramatically. Under lexical static conditions, x is 3, and the value of the program is 3. We'll see that now. It converts our function to a closure. We'll see in dynamic scope why it does that. As we step through, x becomes 3. Now we're looking at a function of 3 plus y. We're able to pass that out. The x equals 20 is essentially useless in static scope. And we eventually get to the value 3. Keeping the same expression, if we change to dynamic scope, we should get to the value 20 because that's the most recent value of x at the call side of f. We extend our closure with x mapped to 3. We pass out the closure. We then extend the same closure environment with x mapped to 20. As we execute the function, we see that we have 20 plus 0 because the most recent value of x is 20, and we get the value 20. We can also show lazy eager evaluation with the same expression. We saw in eager evaluation that the first step takes x equal 1 plus 3, 1 plus 2 becomes x equal 3. If we switch to lazy evaluation, the first step is different. We now actually pass 1 plus 2 as an expression into other parts of the body of the total expression we're evaluating. Now, we may be interested in learning more about the type conditions. Let's look at a simple expression. Consider try 3155 and true. Catch 4448. Let's scoping conditions shouldn't matter. Let's have no type conditions, no conversions rather, and a lazy condition. As we evaluate this, we see that the first step actually immediately comes to 4448. 3155 is a number, and our current type conditions don't allow us to convert numbers to Booleans and expects Boolean operators, or operands, operators. We can also try implicit types. If we send it again, we see in a single step it goes to try true, catch 4448. 3155 is a non-zero number. It's a truthy value. True and something is something, and so we have true. And eventually we get to the value true. Now consider that we have a very large programming language to work with that we called Lettuce. This is the grammar for Lettuce. It can be values. It can be function calls. Given an expression E1, call it with E2. It has try catches, try E1, catch E2. It has conditionals, if E1, E2, else E3. It has let expressions, let identifier X equal E1 and E2. It allows for recursive functions, let rec f equal a function of x, E1 and E2. It allows for binary operations like E1 bop E2. It allows for unary operations, UOP parenthesis E1 parenthesis. The parentheses are here to help with making the parser a bit easier. Some future work could include removing the need to have those parentheses as it can be inconvenient. It does make sense for some of our UOPs like sine, cosine, exponent, and log, but it doesn't seem practical for things like unary negation and knotting. We have many binary operations that we support. As for values, we support numbers, booleans, an undefined value, strings. We support errors, and we support functions. Function of x, e body. X is an identifier for us.
So reflecting on things that did not go as planned or that we would do differently, I think in brainstorming we both had a little bit of the same answer to this question where we would have loved to have spent more time on the design phase before going actually into coding. I can speak for myself, at least in the front end, when I was building these components, it was just kind of a logical progression of which one should go first and then which one after. And because of that, we somewhat deviated a little bit away from our design sketches. I do think that this ended up being a good thing because I am a much bigger fan of our final product than our first initial ideas. And there were a few benefits to the new layout that we made that is easier for students to read top to bottom. But you know, the design phase is probably a really understated emphasis of this whole project. We actually did go through a number of iterations before we landed um, on this. Some difficulties we had was probably in communication between the front end and the back end. It was nothing we couldn't overcome. However, we spent a fair bit amount of time on.
Big challenge was on the back end, we had a really good design about how to evaluate our expressions. Candidly, we were coding that as we were writing up some of the design. However, as we look to implement the idea of expression identification and partial highlighting to make it easier to understand what part of a potentially large expression was reduced, um, this was not doable within the time frame and scope that we had available, in part because we didn't design it correctly to begin with. I think this highlights some challenges in extending products as you design for uh, a part of what you want to accomplish or what you currently know you need for your customer. As you move forward, though, there might be extensions to a product where some OO patterns like a decorator aren't necessarily going to work or be reasonable, and it does require a redesign of the product. Um, I mean, in this particular case, it may just be an algorithm issue, but it might also more require some larger change. So for future applications, something we might want is the ability to create a product where students are given something more like this, where there's some unique code given to them, and they're given a program. I can't do it at the same time, but imagine that we're hiding this right-hand panel that tells students what semantics are being applied, and we give them a code they need to write down. That code is a tracker for us to confirm on the back end what the original semantics are. Students can then write in expressions like so, and using step through evaluation, determine what are the scoping conditions being applied, what are the type conditions being applied. Is this lazy evaluation or is this eager evaluation? There are many programs that would allow you to do it. We might even have students try to come up with a single program that could figure it out. We can also extend for other conditions, other pivots or other types of type conditions. Right now, our implicit type conditions are a lot like JavaScript, but what if we did something more like C or Python, where numbers do count as Booleans, and so on.
So with that, we just want to say thank you for watching, and this has been a very pleasant experience. We've learned so much, and are looking forward to further developing the tool. Keep an eye on the GitHub repository, star it, fork it, and thank you for a nice semester.
Oh, don't forget to like and subscribe. We're aiming for 1 million subscribers by the end of the month.
Thank you.